What are optimizers? Optimizers are algorithms or methods that we use to change the attributes of our neural network, such as weights and learning rate, in order to reduce the losses. So, usually, while training your neural networks, you first mention the number of layers that you want to design in your network, and then finally, while training and compiling the model, you have to mention the optimizer. So as we have already discussed, the training of neural networks works like that. First you pass the input, then after after passing through all the hidden layers, and weights and biases are calculated at different neurons, and after complete feed forward propagation of the features, you try to reduce the loss. So the loss is basically the value that is predicted by our neural network or model versus the actual value. So the way to reduce the loss, or the algorithms or methods that are used to reduce the loss, are optimizers. In deep learning we have different type of optimizers. Let's study about them one by one. So the first one is gradient descent. Gradient descent is the most basic but most used optimization algorithm. It's used heavily in linear regression and classification algorithms. Backpropagation in neural networks also uses a gradient descent algorithm. Gradient descent is a first order optimization algorithm which is dependent on the first order derivative of a loss function. It calculates that which way the weights should be altered so that the function can reach a minima. Through backpropagation, the loss is transferred from one layer to another, and models parameters, also known as weights, are modified depending on the losses so that loss can be minimized. We won't be going in much mathematical details of all these optimization algorithms because behind the normal implementation that we do using our TensorFlow or Keras, there's a lot of heavy and intense mathematics involved in these. So I'll just give you a brief overview, and after that we'll move to the direct implementation of these optimizers or activation functions that we have learned by using TensorFlow and Keras. So this is the first gradient descent algorithm. Now some advantages are like it's very easy computation and we can easily implement it and it's easy to understand. Some disadvantages are like it may trap at local minima. Like weights are changed after calculating gradient on the whole dataset. So if the dataset is too large, then this may take years to converge to the minima, and it requires large memory to calculate gradient of the whole dataset. So what happens? Our main goal to use the optimizers is to reduce the loss. Now if the gradient tries to find the minima of the loss function, then there are two problems that can occur. The first one is the vanishing gradient problem. If the learning rate or alpha that we usually define is too small, then what will happen? The gradient will move very slowly on the loss function graph when it's trying to find the minima. So it may take very long to converge. So this is called the vanishing gradient problem. The other problem that may happen is called exploding gradient problem, in which what will happen, like the learning rate is so huge that the gradient keeps on overshooting, and instead of reaching a local minima point, it keeps on overshooting through the entire graph of the loss function. So these are the main problems with the gradient descent. And next we have is the stochastic gradient descent. It's a variant of gradient descent. It just tries to update the model's parameters more frequently. So basically in this model, parameters are altered after computation of loss on each training sample. So if the dataset contains 1000 rows, SGD will update the model parameters 1000 times in one cycle of dataset. Instead, gradient descent will do it only one time. So if your dataset has 1000 rows, SGD will update the parameters after going through each individual row. But instead, if you use the normal gradient descent, entire 1000 rows will be iterated and then the parameters will be updated. So this is the main difference. Few advantages: frequent updates of model parameters, hence it will converge in less time, and it requires less memory as no need to store the values of the loss function, and we may get new minimas. Now disadvantages, like it is high variance in model parameters because you are constantly updating the parameters after every data point. So that's the reason, and it may shoot even after achieving the global minima, because still it will see the next data point and update the parameters. Now to get the same convergence as gradient descent, it needs to slowly reduce the value of learning rate. The next algorithm that we have is called mini batch gradient descent. It's best among all versions of gradient descent algorithms, It's an improvement on both SGD and standard gradient descent. It updates the model parameters after every batch. So you, instead of either taking the whole data set or just after taking the single data point, you divide the data set into different batches, and after iterating through each batch you update the parameters. So the data set is divided into various batches, and after every batch the parameters are updated. So this is the mini batch gradient descent. This is a slightly better solution from the both extremes of SGD and your normal gradient descent. Few advantages: frequently updates the model parameters and also has less variance and requires medium amount of memory. All type of gradient descent have some challenges. Now, choosing an optimum value of learning rate. If the learning rate is too small, then gradient descent may take ages to converge, that we already discussed. And if we have a constant learning rate for all parameters, then there may be some parameters which we may not want to change at the same rate. So again, we may get trapped at the local minima. The next and probably the most popular and mostly used optimizer is Adam. So Adam is an optimization algorithm that can be used instead of the classical stochastic gradient descent procedure to update network weights iterative based on training data. Adam is different to classical stochastic gradient descent. Stochastic gradient descent maintains a single learning rate, that is alpha, that we discussed. Like if the learning rate is too slow, then it may take years to converge, but if the learning rate is very high, then it may keep on overshooting. So we used standard single learning rate that we termed as alpha in gradient descent for all weight updates, and the learning rate does not change during training. A learning rate is maintained for each network weight parameter and separately adopted as learning unfolds. So some advantages of ADAM: it is very straightforward to implement, and computationally it is very efficient compared to your gradient descent, and we have little memory requirements, and it is invariant to diagonal rescale of gradients. So it is well suited for problems that are large in terms of data or parameters. So this was the disadvantage that we saw in your normal gradient descent algorithms. Again, appropriate for problems with noisy or sparse gradients, so it can also handle these kind of data. Hyperparameters have intuitive interpretation and typically require very little tuning. So these are the few reasons because of why Adam is probably the most popular and widely used optimization algorithm in neural network. So I hope you're clear with the basic concepts of optimization algorithms in neural network. Thank you for watching the video. Now let's move to the next one.